Hi there, and welcome to the CompDaF demo. My name is Georgeo Thanathara, and my group partner is Angus Pearce. This project was supervised by Professor Rob Simmons, Dr. Angus and Ms. Adriana Pinsker.
Dataflow architectures use the principle that a compute node will execute only once all of its direct inputs have completed, and is modeled as a directed acyclic graph, with the nodes acting as functions and the edges as the flow of data.
So CARTA is a cube analysis and rendering tool for astronomy. Our proposed research question was to see whether there is a suitable data flow framework that can be used to replace certain backend features, specifically I/O intensive calculations. We want to see whether these data flow frameworks are scalable and efficient and are capable of being integrated into the current system.
We started off by creating a simple front end that made use of terminal inputs. This was made to mimic CARTA's front end to allow us to standardize the testing by using one client for all three backends. We also made use of the CARTA protocol buffers to serialize the relevant structured data.
So Raftlib is a C++ library that enables for stream processing, a compute paradigm that allows for immediate execution of tasks as soon as the data arrives. Raftlib allows a user to create and write sequential code in kernels. This allows the compartmentalization of state within each compute kernel. These kernels are then linked using stream-like operator overloads, and these linked kernels are added to a map which creates a directed acyclic graph that will be executed. Over here we see the class diagram for the Raftlib implementation. The main class here is the Raftlib class, which creates instances of the custom kernels and will link them and add it to the map for execution. The first image here shows sequential linking. However, the second one is of more interest. Over here we see that kernel B has been replicated 3 times and all the outputs of kernel B has been joined to kernel C. The split operator, which is the less than or equal to sign, maps 3 output ports from kernel A to 3 duplicates of kernel B, which is created during runtime dynamically. The join operator specifies that the 3 duplicated kernels of kernel B is linked to a single kernel C. All this is possible because we have added a Raftlib clone macro to kernel B as well as a copy constructor. A programmer is able to specify what each duplicate kernel requires through its copy constructors. So given the above, these are the features that were implemented using Raftlib: region statistics, channel histogram, and cube histogram. The directed acyclic graphs shown here were generated by the implemented program, which is also useful when it comes to debugging your execution. We tested the region statistics, channel, and cube histogram by comparing the time of execution against CARTA. The region statistics graph shows that the Raftlib computation of statistics performs slightly better than the Cassico implementation. It is evident that for greater file sizes that the Raftlib implementation increases linearly but still performs better than CARTA. The channel and cube histogram shows that the Raftlib histogram was slower than the CARTA histogram. There are several reasons which are presented in the paper, but one that is important is the time taken to sequentially read the rows from the file. As an extension, we began the process of parallelizing the reading of the file using Raftlib, which currently contains some concurrency issues but is not far off from completion. We do strongly believe that implementing parallel reading using Raftlib will reduce the time significantly. From this implementation, we learned that the Dataflow architecture is indeed a suitable model to replace certain backend features of CARTA. We also learned that Raftlib is a well-written library that gives programmers the ability to code within a kernel without having to take into account low-level details of resource mapping or allocation. The results from the experiment did not yield highly in favor of Raftlib, but nor is it purposeless. Some of the current features could be replaced and future features could be implemented in Raftlib due to its sheer simplicity. A limitation that I encountered was, initially we wanted to execute the program and test it on multiple nodes. However, the owner of the library mentioned to me that the code for distributed computing is currently not open source. We know that the library is still being worked on, but its major components are already open source, so we can look for greater improvements in the future.
DALIUGE was designed to drive the processing pipeline for the reduction of interferometric radio astronomy datasets, meaning to process the raw data captured from radio arrays such as the square kilometer array. It is incredibly flexible and scalable, being able to manage itself running hundreds to many thousands of compute nodes at once through its use of various managers. It has already been used in 2 case studies in 2 projects to drive the production pipelines, and has been subjected to extensive testing on its scalability in test cases. It was found that it introduces very little overhead to the pipeline execution while being able to scale from a single node to thousands of compute nodes, with the maximum deployment currently being 1,300 Magnus compute nodes on the Pearce supercomputer. The development team built software objects that they called drops, which differ to the general idea of the Dataflow paradigm in that they are elevated to be entities that can be managed, monitored, and persisted if necessary. The 2 physical forms of drops are application drops and data drops, representing tasks and data respectively. Decentralizing the execution model allows the framework to be highly scalable, since each data drop determines whether and when to trigger the next tasks, which has been shown by tests using millions of nodes. Eagle is the editor for the astronomical graph language environment. It is the visual editor where logical graphs can be created using ready-made components linked together to show the flow of data. These logical graphs are translated by the translator using the provided algorithms into a physical graph, which contains the parameters of the code and the mappings to physical hardware available. This is then deployed to the execution engine, where drops are physically created, linked, and deployed on their specific hardware. The graphs that you see here are the results from the 2 features that were implemented, namely region statistics and region histogram. All testing was performed over the entire image file for a worst-case scenario. The blue bars all represent the same graph and parameters used, while orange bars represent the most optimal graph and parameters used. The gray is CARTA, and it is what we are comparing against. The statistics results achieved a minimum 5 times speedup, maximum 26 times speedup, and an average of around 8 times speedup. This was due to the file not being cached yet, which means it is slow to read using only the disk, and my prototype read the file in parallel while CARTA did not. The histogram results then both made use of the now cached file. CARTA slightly outperforms my prototype, which can be attributed to Python requiring libraries to speed up basic computations, and the way that I had to implement the number library to calculate the histogram added an extra overhead. The documentation at the start of this project was lacking in many areas. The team at ICRA had just released their version 1.0.0 of DALiuGE, and the documentation was not up to date. I worked with Professor Andreas Wickeneck, who gave a lot of help with my use case, in exchange for him being able to update documentation based on my feedback and issues. There are many different ways to implement functionality, with Bash components, C++, Python, Docker applications, etc. This is not a bad thing, but simply opens up a lot of options which can be time-consuming to figure out and test. To conclude, DALiuGE is a very robust and scalable system for data flow that relies on the underlying libraries and tools used. My prototype performed well, but could benefit from being written in C++ or getting more optimization. DALiuGE may also pose more initial work if it were to be integrated into the current CARTA backend, but it is certainly a viable and promising option.